It's trivial to corrupt your repository. And again, because it's over the network, it's rather slow. So these were some of the drawbacks of version control, CDS specifically. So what if we thought about version control not as differences between files, but instead as a snapshot of the file system at a particular state in time? What would that look like? So to answer this question, we're going to build our own version control system using the Bourne shell. Who has used the Bourne shell before? Who has not used the Bourne shell before? Who never raises their hand under any circumstances? Okay, good job. Okay, the Bourne shell is when you open up a terminal on your computer, you may be using like a bash, which is the Bourne again shell. It's a derivative of the Bourne shell. Z shell is a Bourne shell compatible. So here's what we're going to do. We're going to stuff whatever you have left in your hands, because you'll need both hands to type this quickly. Go ahead. I'll wait just 1 minute to let you clone this repository. It will be crucial to your understanding the rest of the presentation. But that's a good idea. Thank you.
Sounds like up there. Yeah.
That's right. Okay. Anyone encountering any difficulties or problems? Okay, good. So CD into the, once you clone that, what this does is it will suck down from GitHub this little repository, change directories into it, and then source, if you're not familiar with the shell, source is a command that essentially executes shell script. And so we're going to source, and don't take my word for it, please feel free to look at that ddc.sh file before you execute unknown shell code on your computer. All we're doing there is defining a few aliases that we'll be using later in the presentation. The presentation is largely about defining these aliases, so that's what we'll be doing. Okay. So if we were making our own repository, we need a place to put copies of our files. Now don't do this. This is what the sample means. Don't actually do this. So we're going to call our repository ddc shell. Is what I'm going to call it, ddcsh. And so test repo is where our source code is. I should have called it source code or something like that. And inside there, like we do in CBS or in Git or Mercurial, most version control systems store at the root of your project where things live. That's our repository. So this is the init function. So Git has an initialize function. Most version control systems have some kind of initialization to set that up. In this case, we accept a path here, and as $1. So we're going to say on our shell at the command line init and then a path name. If the path is not a directory, we're just going to print a friendly message and return it. Otherwise, we're going to change directories into that path. We're going to set an environment variable that will be used by the rest of our functions tonight, shell functions. We're going to create the objects directory. That's where we're going to store all of our backups. And we're going to print a friendly message out. Now, I should point out that I'm not a professional Bourne shell programmer. This may be good. It may be not. That's for you to decide. I'm not putting this out there as a good example of Bourne shell, but it works for me. So So we can do this. If you've sourced dbc shell.sh, you can run these commands now. Please do so. One or the other, they're the same. Let's make a directory called test repo, and then you can just say init test repo, and what will happen is it will cd into it and then create the .dbc shell. So this, in a picture, this is what we have. The beige box is our test repository, you can imagine that. And inside that we have another directory called dbc shell, and inside of that directory we have a directory called objects. So we want to add content to our repository now, right? We've made some changes to a file. So don't do this. Let's pretend this is it could be source code, it could be a document, it could be anything really, it doesn't matter. But we've got it, and it's called some-file there. And now, how would we make a backup of this file? We could do it like CVS does it and just copy this file into the repository. But then we have problems. What are the problems with that? What are the same problems that CVS has? So you start, let's say we've copied it into the repository, now we've made changes, we copy those changes in again, but now it's just clobbered the file that we had in there, so we need to call it something different, like maybe .1 or something. What if the file was already called something .1? Now we're .1.1, I don't know. You would run into all kinds of versioning problems when you do that. What if we came up with a unique identifier for the file, a UUID? That could work. But consider this. Here's something interesting. Who's familiar with the SHA algorithm, secure hash algorithm? SHA-SUM, any of those? Okay. SHA is it's a one-way hash function. It takes the contents of the file, runs it through an algorithm, and comes up with a unique string that identifies the contents of that file. You can't go backward and get the file again because it's usually a compressed little, 16 or 64 bytes, something like that. But it gives you a unique signature for a file. So what if we took the SHA of our file and used that for the file name inside the repository? Something like this. And this. So we come up with the SHA-SUM, and we take that long string there, and then we use that long string as the name of the object in the repository. This has some really interesting side effects. One of them is that we won't ever have any duplicate files. If we happen to have several copies of the same file throughout our source code, it would only be in there once, because this hash will always be the same, no matter what the name of the file is. The contents are identical, and so it all has the same hash. The other nice side effect is that we can always tell when this file has been tampered with. If somebody goes into the repository, or it might not be malicious, it might be just an accident, or a partial download, maybe something failed. It gives us a checksum. It enables us to look at the file itself in the repository, and it's this long string here, 0e, that's its name. And what we do is we take that file and we run it through the SHA-SUM algorithm again, and it should give us exactly the same thing. And if those two things are not the same, that means the file has changed. So this gives us a layer of security built into the repository. It's a very nice effect. So what we're going to do is now we're going to, we've written add that, we've written initialization. Now we're going to write add. Here are our two functions in our shell script. You can find these in the dbc.sh file if you like. But here they are on the screen. Hash object is a little helper function we have. All it does is it takes the name of the file and returns its SHA hash. Now I have to do that funny thing with awk because it returns the name of the file along with the hash, and we just need the hash. We already know what the file is named. Add, this is our add function. This is what adds the file into the repository. It makes use of that hash file. It takes the SHA here, and then it copies the file that we gave it into the repository under that name of its hash. And if I'm going too fast, or I'm unclear on something, please feel free to interrupt and ask a question. I don't mean this to be just monologuing. really want everyone to make sure that they are clear on this. Sometimes I get going a little too fast, according to my family. So, questions? So, add content. So, go ahead and do this now. Let's create some file, and please use the same strings. And you'll see why in just a few minutes. So echo, quote, some space file, quote, angle bracket, some dash file. And then we'll run the add. Add is our shell function that we've defined. So once you've done that, let's run these commands on in your terminal. SHA-SUM may not be defined in your distro. It might be SHA-1 or some other thing. Just type SHA and tab. See if you get some tab completion help to figure out the SHA algorithm on your shell. So what did we come up with right here? Just read me the first four characters.
0, E, 0, E.
Okay, that's good. Did anyone get anything different than that? We all got the same thing. That's because that string, some space file, hashes to 0B08 or whatever it is. You'll find in DBC shell, type F, that means we'll just be looking for files. What did you find?
The path objects slash and the hash.
That big long hash. All right, that's what our add function did. It took the hash key and copied that file. Cat that file. It's a copy of that of some files now. So we've just created, we've just added something into our repository. Here's a picture of what we've done. In our test repo, we have some dash file. When we did a add, it hashed it and put a copy of that file in there and named it by its hash. This is called content addressable. This is a fancy term that just means that the name of the file, or if the file is found by its contents, by the contents. So this is good. We've got now, we can add files all day long, and every time we change a file, we get a new file that is stored in there. And it will be safe in there. There's still a problem though, right? How do we get stuff back out? So we just renamed it. We have no idea how to get it out now. It's like a bucket that we can't look into when we're trying to pull something back out of it. There's a second problem. Let's say we're just working with the one file. We add that file, we make a change to it, we add it again. It's going to have a different SHA hash. We change the file again, we get a new SHA hash, and we go looking for, we want the most recent one, whatever. We don't know which one is the most recent one. We can look at the timestamps maybe, but let's say we cloned this from somebody else and all the timestamps are the same. So these are the two problems that we're going to solve next. The first one is indexing content. We need to know how to find something, what we're looking for, based on its original file name. So here's some code. What we've done is, the first part of add, those 3 lines are the same. It's this bottom chunk here that we've added now. I'm going to gloss over this right here. This isn't the important part. So the first time we add a file, index will not exist, and so we're just going to skip right to here. We're going to take the hash, and this is a tab character, and we're going to take the file name and a new line, and we're going to append that to a file called index.tmp. If that file doesn't exist, it will be created for us right then and there. Then we're going to rename that file to be DBC shell index. So this is nice. If we were to add the file again a second time, let's say we make changes to the file and we add the file again, the second time, index will exist, won't it? So because it exists, now we're going to, who's used grep or egrep? That's familiar to you in Unix? What does it do?
Searches for regular expression through files.
Yes, it searches files for lines matching a pattern, right? This V flag here inverts the sense of that, so it will print out all the lines that do not match. So what this does, this is sort of a poor man's subtraction. What this does is it takes the last time this entry was in the file and removes it from the output, and then we copy that to index temp. So this way, this enables us to add a file multiple times but not get multiple entries in the index. We just get one entry. That's all that is. It's not nothing that special. So now go ahead and type this. Let's add some file, and now you can cat the index, and you should see exactly that. Does anyone see anything different from that? That look good? So what we've done, this is what we had before. Now that we've done an index, we have a new file up in .dbc shell, and it contains, I've got a colon there, just ignore that. We've got the hash and its name. So now we have an index of how to find things in our repository. So if I want to pull out some file, I know, oh, that's the 0E08B5 object, or blob, in the objects directory. And then we can copy that back out. So now we have a way to put things in and pull things out. Do you remember our second problem? That was one of history, right? We didn't know which one comes first. If we've done this multiple times, there'll be multiple blobs or objects, but only one entry in the index. So we need to record history. We need a way to record the state of the index over time, and that's what this is the new function we're defining called commit. What we do here is we take the SHA, or the hash of the index, and we copy it into the objects repository also, or the directory. So now the index itself is version control, tracking the state of the index over time. The next thing we do is we make what's called, we'll call it a commit file or a commit object, and we copy the index's hash into that commit object, the date, a parent, we'll get to this later, and comment, right? Anytime you want to commit files, you want to say what you did in that, for that change. I changed this line, or I added this, or whatever. And then finally, we add the commit object itself, the commit file itself as an object in the repository. And then the last thing we do is we echo this commit object, its hash, into a file called head. And why is that useful? Head always contains now the most recent commit ID, the most recent ID of the ID of the most recent commit. That way we can make use of it right here. If there was a commit before the commit we just made, if we've had other commits, the one right before us is stored in head, and that becomes our parent. We'll make use of this in just a moment here. So please go ahead and type commit, first commit. So here's our file in our index. When we run commit, we copy the index into the objects directory, and it gets its own hash here. That's its name in the objects directory. And then we create a commit file. Now the commit file will probably be different because I ran mine at a certain date and you ran yours at a different date, and that is part of the hash, and so it's going to be different. But the index should match, and the sum file should match. And then we point head to be at our most recent commit, so that we can always find. If I want to find what was the most recent commit, I can just cat out whatever's in head, and I've got it. So let's look around a little bit now. Go ahead and type these two commands. You'll see in there the head and more objects in there, right? When you type head objects, you should see our original file, some file, the index will be in there, and also the commit object is in there. Anybody see any problems or anything different? So you may be saying to yourself, Scott, this is great, but if, this is great if you have like a flat directory, can this handle subdirectories? Well, let's try it. Go ahead and type these commands here. We'll make a subdirectory called subdir in our test repo, and we'll create a file inside of it called subdir/sub-file. and then we will run add on it. We go. So this is where we were. Watch down here next to the sub file. We create our subdir and sub file, and then when we run add, two things are going to happen. We're going to get a new object, a new blob for sub file, and we'll get a new index entry. And there they are. Does anyone have anything different than 94? Good. So when we add that file to the repo, when we added this, its entire path is added to the index. This is nice because if we want to ever do like a checkout, we know what directories to create and where to put things. So this handles hierarchies just fine as well. So go ahead and let's make a second commit. So, and while you're doing that, let's talk about history a moment. Remember that when we make a commit, we're doing a couple of things. We add an index to the repository as if it were another file we're committing. And then we add the commit object with a pointer to that index at that point in time. And a pointer to the previous commit. So it's like this. Here's where we are right now. We've got the index ready to go. We've got the new file there. When we type commit, second commit, the index is pulled into the repository. A new commit object is made that points to that index, so that at this point in time, this is what our repository looked like. At this point in time, this is what our repository looked at. What does it look like right now? We look at head, and it points to this commit right here. What did it look like before then? We just go to the previous one. So we now have a complete history. We know where to start. And because we've got a pointer to the, we also have a pointer to the previous commit. The first one doesn't have anything that had no parent. So that's the end. This is called a DAG. What's a DAG?
You're an acyclic graph.
Excellent.
Which is like a tree, but the branches converge again.
Acyclic though, so they cannot merge again.
Well, they converge like a diamond, not like a cycle.
Right, yes. So, so this is what we have. We have a directed acyclical graph, which means that we can traverse it and have a perfect view of our history here. So go ahead and type these commands. You'll see three new objects. You'll see the subdir, the new index, and the new commit object. And then head. Go ahead and cat head. Head will be your commit ID will be different than my commit ID. But so now we have a new commit ID. And this is the last function we'll talk about tonight. In terms of this BBC shell. So if we want to view our history now, because this is a DAG, we look for the head. If there's no head, it means we haven't made any commits yet. If there is a head, we're going to read out whatever commit ID that was in there, the SHA, and then we're going to set a path variable that points to that so we can look at it. Then we're going to enter a little loop here. This says while the SHA string is non-zero, and it has some length, this is just a little Bourne shell thing, we're going to do these things. So as long as the SHA variable has something in it, we're going to keep doing this. We're going to print out the commit, we're going to print the date, we're going to print the comment, we're pulling stuff out of that commit object that we had so that we have like a nice log. And then what we're going to do is we're going to look at the parent in that commit object. And we're going to set that to our new SHA. We're going to reset our path variable, and we're going back to the top of the loop. Is this still non-zero? It is. So we do it again. And now we're on our first commit. First commit does not have a parent. And so this will be empty. We'll get to here, and we exit out. Go ahead and you can type log. Go ahead and type log. You should get a Git-looking kind of commit history. Does that work? So we have just implemented 80% of what makes Git special using the Bourne shell. You can probably imagine a few different ways to implement a diff. How would you implement diff? Like, as in Git diff.
So we,
Type in vendor.
Yeah. What were you saying?
well, so we have our current file, and we want to know if it's like a certain commit.
Yeah.
Yeah, so we can just look up either commit ID, or I guess we could go through that tree and look, is that file, was it committed during that time, just since we have.
Exactly. Yeah, you give it a commit ID, you find the commit ID, look at the tree, and you look at the index, the file name. What about, you could do tags, checkout. Checkout would be essentially wiping your working directory and pulling things out of the repository at a certain point in time based on that commit ID. You just look at whatever index was committed at that time, pull the files out and rename them. Status, see what's different from what's in the repository right now, what new files that are not in the repository. So we could implement the rest of Git going down this road if we want to. So good job. So let's talk about Git. Git's easy. Okay, please, let's get out of our test repo now. You can blow it away or whatever, but we need to be out of it. If you close your shell, those shell functions that we sourced earlier will no longer be visible, and that's probably what you want to do. They won't be useful to the rest of the meeting. So do this now. So once you're out of the test-repo directory, let's make a new one. It doesn't matter what you call it. Go into it, type git init, and we're going to remove the hooks directory. It's not harmful. There's nothing in there right now except a bunch of placeholder scripts, and they just kind of clutter what we'll be doing today. So just for the sake of discussion, just go ahead and blow that away. Just be a distraction. I'm going to mention a few times explore the space. And when I say explore the space, this is what I mean. We're going to look at what does head have in it. We're going to git head. We're going to see if there are any refs. And we'll talk about what refs are maybe. What does the index look like? And some of these commands are what in the Git world we call plumbing. There's plumbing and porcelain. Plumbing are the commands that you don't use on a day-to-day basis, but are useful for exploring how Git works. And the porcelain ones are that you would use day-to-day in your work or school or whatever you're doing. ls files is definitely a plumbing command. Are there any objects? So we're going to use the find Unix command. And what are the contents of a certain object? Cat file is another plumbing command that you don't use on a daily basis. -p stands for pretty print. So that gives you, the objects in Git are compressed to save space, and so they wouldn't be very useful if you were just catted out like we did in our PVC shell. But cat file knows how to uncompress them and present them in a nice way for us. So in Git, we're going to add some files now. Please go ahead and type this. Again, exactly, so that we all get the same hashes. And go ahead and add that file to your repository. And then do this. You should see this. Does anyone not see that? Everyone sees the same hash. In Git, Git takes the hash. It doesn't use the SHA. Well, I don't know exactly what SHA algorithm it uses. It uses something SHA-ish. But I think it's probably after compression and some other things. I think it might add a header. These first two characters are part of the hash. But to avoid hitting the Linux default 16,000 files per directory, it uses the first two letters of the hash and creates a directory, and that sort of spreads things out a little bit. just so it's not all. But that is part of the hash, the FD there. Let's see what else we've got. Okay, so go ahead and type this, get cat file. Remember, it starts with FD48OB. And we should see the contents of the thing we just added. And if you do a ls files, these are terrible. I will go on record as saying Git has a horrible user interface. It has command line options that are secret and crazy and do almost the opposite of what another command line option you know on the same command does. Anyway, you just gotta live with that, okay? So git ls files -s stands for staged. In other commands, it's cache, but they mean the same thing. They mean look at the index. You should see this. This is the permission. So git is nice because it records the file permissions 644. The hash of the object we added. I do not know what the 0 is, and then the name of the file. And then go ahead and type head git refs master. You should see this. Doesn't exist yet. Master, in Git, there's the notion of what's called a branch. A branch is simply a pointer to history. We haven't made any history yet. We've just added something to the repository. We haven't committed it as part of our history, so there's nothing to point to yet. So in a picture, it looks like this. This is the inside of the .git directory. And you can, with a find, you can see these same things. I'm not going to be talking about the working directory at all. You've got head that points to master. Master doesn't point to anything. We've got our index there that we looked at with the ls-s. And then we've got objects that we looked at with cat file. So we've added a file to our repository. We're going to update that file now. So it used to say a good file. So go ahead and clobber it now. Say echo some file, it's some dash file. And add it. And do another find. Am I moving too fast? Okay.
I didn't miss, did we commit something? We didn't commit.
No commits yet.
Okay, I thought I missed something on the slide.
If you see 2 lines, and that's all, you haven't missed anything. Does anyone see anything different than that? You're a good typist. Every time I give this, there's somebody who doesn't use the quotes or something like that. All right, so let's cat file. Should be some file. Oh, it looks like I actually did the whole long command on this one. Oops. When does it do that? That's working for me. You can see that the index has changed. It used to have FD 48OB in it, and now it has 7816. Because we've added that, and Git does the same thing DBC shell does. It only adds it once to the index. So we have this. You can see that the index changed, and we've added a new blob to our objects directory. The index only tracks the latest change on the file. So adding files does this. It creates a new blob in the objects directory and adds the hash of the blob and the path of the file to the index. That's add. That's all it does. Rename a file. Let's create a new file called another file and add it. Go ahead and we'll add it to the repo. Let's look at the index. We should see 2 things in the index now. Both of the ones we've added. And then let's run this command. Move is like the Unix move, it just renames a file. So we're going to rename another file to wonder file. And there's no output typically from that. We'll do git ls files again. So there's our old sum file. And you should see now Wonder file. Does anyone see not this? Anything different? So this is what move does in the picture. We add a new file, and it's in the index. Now watch the index again. When we run a git move, it just changes what's in the index. There's no new blobs created, nothing else like that. So this is git move. Changes the name, the working directory, and updates the index, and that's it. No new blobs. Removing the file. Let's get rid of that one. Git rm wonder file. Sorry, I'm going to do that one really fast. So watch the index. It's gone. But the object is still there in the repository. So that's what rm does. It removes the entry from the index and also your working directory. It's gone. But you still have the file in the blob is still there. If you pass the cache option to rm, it only removes it from the index but leaves it in your working directory. This is usually what you want to do. Default, what you got to read the man. You got to read the man pages or your host. Typically, when you add something by accident, you want to undo the index part of it, but not blow away the file that you added. Maybe you do, but I'm just saying, be aware that there's a difference there. Yes?
What does git rm keep the object file?
Git wants to preserve a history of everything. If that object had been pointed to by some other index, maybe, or something else, it might not be in the current index, but it may be in use by, by some other, some previous history or something like that.
So is there some information left to fix something stupid you did?
Possibly, yeah. It tries to be default to the safe, to being safe. Oh, I just blew away this. I didn't know it was going to do that. Like if you type this, I didn't know it was going to blow my file away from my directory too. That was rm. Well, it's actually still there, so you could pull it back out if you knew how to look for it.
It makes it look like git rm cache would also keep the object.
It does. Yeah, both of these, neither of these remove the blob. The object always stays. Good question. Was there any over here? Okay. So these two are almost inverse, but not quite. Adding creates a blob and adds the blob hash and file into the index. Git rm cache removes the index entry, but doesn't remove the blob. So they're not quite inverse. You still get that blob side effect. So now we know how to add, rename, remove things from the Git repository. Let's talk about recording history. Go ahead and cat head to see that it has refs head master. And we cat this, we'll get the no such file directory. So let's make some history. Go ahead and please type this, git commit -m first commit, or the comment doesn't matter. You're going to have a different commit ID. Does that work for everyone? Is there any problems with that? Sometimes it prompts you. If you've never used Git, it might ask you to set your username or something. You'll get something kind of like this. Your hash will be different from mine, but you'll see master, root commit, your hash ID, comment that you put in, what happened, you changed one file, added one file, and the mode, the Unix file system permissions that were recorded with that file. Let's see. Okay, now go ahead and git head. It should still say refs head master. Now if you look at refs head master, you should see the same ID that your commit gave you in short form. This is our first commit. So now if we look at head points to the branch points to the first commit. That's kind of cool. So, oh yeah, git cat file -p. So you can look at commit objects as well. So use the commit ID that you had from your previous action when you added it. There will be a tree. I'm curious, does everyone have 508D? Does anyone have something not 508D? Okay, that's good. That means that the names of our files are the same and the contents of our files are the same. So the tree object sort of is like our DBC shell index, but it's on a per directory basis. We'll get into that later. We'll talk about trees. Should have an author, a committer, timestamp of when something happened, and then first commit. So this is kind of the raw output of a commit object. You can cat file all kinds of interesting things. But it turns out there's only 4 interesting things, kinds of interesting things. There's blobs, trees, commits, and something else that I'm forgetting. So,
Committers,
committers.
trying to find US commit.
I don't know if those would be unique objects in there. Anyway, let's see. So this is where we were. We've added another file, some file in our index. When we run commit, what we do is we create a tree object. We'll talk about tree objects in a moment, that points to whatever's in its working directory, in that current directory for that. What that is in the root, in this case, is a repository. The commit object points to the tree, and the branch file just has the ID of the latest commit in it. So if you cat the tree object, you'll see the index as it existed at that time of that commit. So commit does a couple of things. It creates a tree object, which is like a per directory index. It creates a commit object that points to that tree and the previous parent commit. And it points the branch to this last commit. It works a lot like how our DBC shell works. So here, this was a tree object. Go ahead and type these commands. Make your subdir, and we're going to echo some file in the subdir again. Your finger should have that muscle memory on this one. Now, before we add it or do anything else to the file, there's another plumbing command that we can play with called #-object. And what it will do is it will run that file through Git's internal hashing algorithm and tell you what it would be called if you were to add it into the repository. That can be handy sometimes. Or if you have a file and you want to know if it's already in there, I guess this is one way to do it. Should look like that if you have the same subspace file in there as I do. And now let's go ahead and add it. And if you do an ls files-s, you'll see there's our original file that we added, and here is the subfile. So this is our index. So what we've done is we've gone from this, and when we added a new subdirectory and added subfile, you can see it's in the index now, and we've got a new blob. Now let's make a second commit, and we can start looking at tree objects. You can use any comment you like. Again, you'll get a, it doesn't say root commit anymore because we've already got one commit on it. But this is another commit. You'll have a different hash ID than I do, commit ID. So when we create a commit, remember it creates a tree object. The tree object is a per directory index. So this tree right here contains a pointer to some file, which is in its working directory, and also a pointer to this tree object. This tree represents subdir. Every directory gets a tree object in the hierarchy. And that one is the one that points to subfile. And we have a commit that points to the root tree and to its parent. And the master has been updated, the branch has been updated to point to the most recent commit. So go ahead and we can cat file this new tree object. It contains some file, which the previous tree did, but it also has a new one. And so the contents of this hash to be 23b36f. And we can cat that, this here is this. We can cat that tree and see that it contains subfile. So trees represent the state of the working directory at a point in time and point to blobs and other trees. And that's all a tree is. It's a flat file that points to everything that's in this directory, including other directories that are in it. And commits points to the root tree only. So that's easy. Again, we extend our directive acyclical graph analogy. That is a tree, and that is a commit. So we'll talk about branches just briefly. Go ahead and type this command here. Git branch, my branch. I don't think it does any output. If you type git branch now, by default it will list your branches that you have. You should see something like this. The asterisk indicates this is the current branch that you're on. Then you've just created a new branch called my branch. The asterisk is just your active branch. Go ahead and type head.git refs head star. You should see, whoops. I don't want to go that fast. You should see all that. Both master and my branch point to the same commit. So in a picture, it looks like this. Here's where we were when we said git branch, my branch. We create a new branch. And it's just like master. It's a copy of master. This is why branching in Git is amazing, because all you're making is a little file with a commit ID in it. Branching is super cheap. It costs about 32 bytes and one syscall. It's extremely fast. And that's it. Head hasn't changed. Nothing's changed. We just have a new pointer in our branches, in our refs. So let's check out my branch. Git check out my branch. Now go ahead and cat git head. You see that it's changed to my branch. So when you do a checkout, those are the things that happens. It changes what head points to. So watch this right here. We're going to check out. Boom. That's it. That's all that happens. That was really easy. Now, there's more that happens, and we'll talk about that in just a second. When you check out, also, what you get is the Git crawls this tree recursively and makes sure that it matches, or that the working directory matches it. So if there are any files in the working directory that are not found in that tree, but that maybe were part of the commit history, it will remove them. It won't remove files that it doesn't know about. But it will remove files that have been removed in subsequent commits, for example. So it essentially pulls everything out, starting from here, recursing all the way down to the bottom of all the trees, and pulling it out into the working directory and making it match. In DDC shell, we didn't have trees, but we had the same effect with just the one index top. We could have made it work the same. Git does trees for a number of optimization reasons. Okay, so let's make now a new file. We'll call it branch file, and add it. So here's what we're going to see. We're going to see a new object with branch file, and we're going to see a new entry in the index. There they are, branch file and branch file. We added it. That's all add does. New blob, new entry in the index. Let's make a third commit now. So we've got our index, we've got our branch file. What does a commit do? It makes a tree object that points to the state of the repository at that point in time, and a commit object that points to that tree. There they are. This is the new tree object. It points to the same things that the previous root tree object pointed to, namely this, and I had to kind of go around. That 7A1 thing is still there, but there's the new file here that's part of this branch that we've also added, and then we have a new commit, that points to that tree, and that's it. We've now split our history, as it were. These things are not accessible to this branch because this is directed. The arrows never go this way. They always point to the parent. This is pretty much the bulk of my presentation. We can talk about resets for a second. This is a reset. When I say git reset, what happens is it changes what this points to. And then, depending on if you're doing --soft, --mixed, or --hard, it will change the state of the index, the repository, working directory, things like that. But that's all a reset is doing, is it's changing what branch points to. The ref head, my branch, or ref head master. So reset moves that pointer around. Let's see. This is kind of interesting. So it's kind of like going back before a commit, but after an add, because you still have all this stuff in there. It's just no longer accessible now. Unless you explicitly say, git reset my branch 1484 BAF, and then it will point the thing back to where it was. So you can move that pointer around just by using the reset command. That's all you're doing. And then hard and mixed do various things with the working directory and the index. So use them sparingly. Make sure you read the man page. So that is Git. I have 3 slides left. Checkout just changes the branch that head points to. We've already seen how that works. And then updates the working directory. Fetch is a command you might have used in Git. All fetch does is it pulls down all the objects, including trees, commits, and blobs from a remote repository. I mean, it might be on the same disk or whatever, but it's, as far as Git's concerned, it's somewhere else. That's all fetch does, just pulling it down, pulling all those blobs and trees down. It doesn't do anything else. A merge is a commit with 2 parents. So if you have 2 lines of history now that you pulled down from one, a merge is a commit that points to 2 things like this. And both lines are now merged in that one commit. A pull is a fetch plus a merge. A clone is an init plus a fetch plus a checkout. So when you did a git clone earlier, that's all you were doing. You did an init in a directory, pulled all the objects down, and checked out a certain branch. Rebase changes this is complex, but it's extremely useful. It changes the tail, that is the first commit of when you have a history, when you've made what's called a branch, it's sort of a fork in history. It takes that first commit of the fork is what we call the tail. And it points it to the head of your working branch. So if you were on this branch here, and you have this second branch up here, if you were to rebase this one onto this one, it takes this and moves it to the end of your main history and points to its parent as the last commit, or the most recent commit on the branch. So that's a rebase. Garbage collect and prune, find and remove those unreachable objects. Did you notice in our repository we had a couple of blobs that nothing pointed to? GC and prune will find those and remove them, and it's a way to tidy up your repository. After you've done lots of fetches and pulls and merges and things, after a few months, things kind of get a little crispy like that, and this will help clean things up. Git, you'll find if you have ever cloned a large repository, has something called pack files, and those are basically tarballs full of blobs. It uses it for efficiency over the network. You don't have to keep opening up TCP sockets and pulling new things. You just get a whole truckload of objects that somehow relate to each other, and it's just a space-saving device. And you'll need to be aware of that. It's not, so the way I've presented Git is a little simplistic. And the reality of Git, they've put tons of optimizations in there to make it fast. And pack files are one of them. So that is it. These are my sources for tonight. Any questions I can answer? Yes?
So I've heard that Git can't track empty directories. Do you know why that was?
So to Git, it goes back to trees. Remember what a tree is? A tree is it's a file that holds a pointer to any of the blobs, meaning actual files in it, in that directory, and other trees. So a tree doesn't exist until there's a blob in it. So if you have a subdirectory, as far as Git's concerned, it doesn't exist until there's something in it. It's just the way Git was designed. It's not pointing to subdirectories, it's pointing to trees. And trees are only created when there's something in it to point that tree can point to. But what you would have would be an empty tree, a tree that points to nothing. And it has. They could probably figure out a way to do it. I'm thinking I could probably. You could say git add directory name. It would say, well, this is a directory. I don't create a blob for directories, and I don't add them to the index. And when you commit, it looks at what's in the index, and there's nothing there because you haven't added anything. And that's why it goes back to, it really wants to deal with files and trees, blobs and trees.
What are the use cases for an empty directory?
Like if you want to clone like an entire file system, in Linux there's var empty, that is an empty directory that is guaranteed to be empty. That's kind of the promise of the operating system. Or if you want to preserve some structure to be used later. I've come into a number of cases in my career where it sure would have been nice to do that.
Just drop on it, file in there or something.
Yeah,
You drop a dot get ignore, typically.
this is Carson. I've worked with Carson for years. He is a master at Git.
Wow.
Um,
I'm mastering something.
Yeah, I put a git ignore in there, which means that when it gets checked out, just the directory will get checked out. Other questions?
Why was it named Git?
Linus said so. I don't know. He's spoken a little bit about that. He thought it was kind of stupid. He was in a bad mood. He was dealing with. Well, there's bad and worse. He was dealing with, I think it was Bazaar, was the version control system he was using for Linux at the time. And the Bazaar project was changing its licensing. I won't go into a lot of the details, but he was frustrated, and I think it was a long plane flight or over a weekend or something like that. He thought of this idea of how to do it, and he wrote Git. I think Git will be as much of a legacy as Linux. It's really a brilliant design. The user interface is horrible, but the design is amazing. It's very clever.
That's exactly the way I feel right there. It's brilliant with the user interface. Is there ever been any effort to clean that up or maybe do a better one? There's several projects. It's just confusing.
It's surprising is what it is.
The older you get, the harder it is to learn Git for some reason. I don't know.
That may be.
I don't know.
Yeah, I don't know. I had to come up with, I had to teach, well, I used Git and I was considered a Git expert. And I always thought, you've heard of imposter syndrome? I don't know what I'm doing here. And, but putting these kinds of presentations together has helped kind of solidify a few things. I don't know if I put it in here. I didn't. There's another project, I can't remember her name, Rose something, I believe, implemented Git in JavaScript, which is also a very enlightening project to look for. Just look for Rose, Git, JavaScript, or something like that. And that was sort of a seminal moment for me to realize Git is not that complex under the hood. It's very simple, but again, the user interface with just slapdash, too many cooks. Mercurial is a beautifully designed version control system. If you like the distributed nature of Git and all the cool things it does, Mercurial is just a beautiful one. It's better. Anything else? Other questions? Thanks very much.